Okay, hello and welcome to my channel. Today it's gonna be part 2 of finite square wave potential, and today we will talk about unit-free numbers. So in quantum mechanics, you're gonna see unit-free numbers a bunch of times. These are gonna be extremely helpful for you as you don't really want to deal with all sorts of unit. Those could get messy real fast. So for you to get unit-free numbers in finite square wave potential system, it would be starting with adding the two, to K. You get more specifically K and kappa. So let's do that right here. Let's add these together. And what would you get? You would get, well, what would get eliminated here? Both have E, but only the inside part got the V naught. So sum would be 2m h bar with just V naught. Alright. Next, we would like to put in a square. A square. So here it would become 2m v naught a square h bar square. And we put in the a square to eliminate that unit. So there we go, you got something that is unit free. And for this to be more condensed, more easier to use, let's get notation for these guys. So let's say that this is the inside, so I'll write it as eta. The outside is psi. This guy is z naught. These are all square. And eta and psi are positive. And z naught squared is equal to that. So there we go. These are the unit-free numbers you would be using in a finite square wave potential system. And now we're gonna move on to solving this guy, actually. So first, let's find our energy state. No, not really. Not there yet, but let's get our wave function first. So let's apply the conditions. So for your wave function, so for psi to be, can you see this? Be continuous. The interior has to match with the exterior, right? So in matches out. You don't see this in the infinite square wave problem, but you're gonna encounter this thing, from now on. You're gonna encounter this part. You gotta match the wave function and the derivative of the wave function at points. So let's start with your wave function. So for it to be continuous, so psi continuous, we're going to take A. That's the only necessary part. Okay. Interior, we're going to consider, only consider the odd part, even part. So, no need for the coefficient. Cosine Ka is equal to A e to the minus kappa A. Next is your derivative. And as above, only needed at a. Okay. Derivative here. Kappa. Okay, that is okay. What am I doing? Okay, you got this. The standard procedure would be dividing those two. Let's do that right now. So minus. And now we're gonna divide it to get tangent. So after dividing this, okay, I should have written it as kappa A. So dividing would eliminate these, and what you're left with is K tangent Ka is equal to minus kappa. Oh no, I eliminate the minus here, so no more minus. So what you get ultimately is that K tangent Ka is equal to kappa. And now you would want to put these into our unit-free numbers. So let's throw in an A. So that would yield us Ka tangent Ka to kappa A. And remember, Ka is eta. So eta tangent eta is equal to psi. There we go. This is what you get. And now let's take a look at, well, psi squared, as we would kind of want to put it in the form that you can see the graph that I have to show you guys. Let's erase this part. So let's take a look at psi square, that is kappa square A square. Right, so from here, you expand this. Okay, no. From that to this, you can get this, you can turn this into your K square instead. So that would equal to 2m EA square over h bar square. Now you would want to sort of isolate the energy out. So now you can write this as that you would want as many unit-free number there as possible. And this guy, as you can recognize, is z0 squared. So ultimately you get E over V0 is equal to psi squared over Z0 squared. Yep, this is what you get ultimately, and from this you can plot a plot of psi and eta here. Plot a plot of psi and eta for odd and even. That's psi and eta. Eta. These are two graphs for odd and even. So this would follow, okay, the tangent. Pi over 2, 3 pi over 2, 2 pi. So with even tangent, it's going to start from here to here. So it's gonna be that it would kiss this line right here, the pi over 2, the 3 pi over 2, and the 5 pi over 2 here if I draw this, but I'm not gonna. And the picture here you would get is some sort of circle with the radius z0. And let's do the same with the odd one. The odd one is gonna start from pi over 2. And it's gonna kiss this line. There we go. There would be a circle that is radius of c0 as well. So in here, this one eta is, psi is equal to eta tan eta. And in the odd part, eta is equal to minus eta cot eta. And you can see here, as this line here started from the origin, it would guarantee that this circle would cross one of the line, right? And every time it crosses, that means that there is a bound state there. So if you have a circle like this, that would mean the system has one bound state. If you have a circle like that, that means that the system has two bound states. So every time the circle crossed the tangent, that would means one bound state. And so as I said, the tangent here started at the origin. That means no matter how small your radius is, it would guarantee a bound state. So there would always be an even bound state in the finite square wave potential. But on the other hand, when you take a look at the odd one, you can see that it started from pi over 2, meaning that if your radius is small like these, there would be no odd states, no odd bound states. So we can say here that the even state is always guaranteed in finite square wave potential, and odd is not. Well, because if you remember, the even state is the ground state, or okay, I'm sorry, the ground state is an even state. So yeah, that's it for today, and goodbye.